Hello again, and my apologies. I think due to some technical issue, my video got interrupted. So let's continue from where I video got stopped. So again, I'm sharing my slides. Just wait for a minute. So I think we were discussing about the controlled source seismology. So yes, so here we are. So as I was saying that the top one section is the seismic data, and the below one is the interrupted seismic section. So here you can clearly see that how we, with the help of seismic data we can clearly demarcate the salt structure that is present in the subsurface. Also, the fault is pretty much evident with the help of seismic data, and you might be wondering that in this image it's not like in that seismic image it's not clearly visible, but yes, when we apply some attributes and enhance the section and see it in a more visualized manner, then all those features are pretty much clear. And similarly, here also we can see some unconformity that is I can also see in this seismic section. Let me start my point. Okay, so now so what's the application of this like controlled source seismology? So it includes two type of method: reflection and sorry for this mistake, it should be reflection and diffraction. So it also help us to map the crust and the upper mantle. So sorry, as I mentioned earlier, that due to the limitation of the length of the geophone array, we can go up to the upper mantle, and this controlled source seismology also help us to explore the oil and gas provenances, or help in to conduct the geotechnical study where it helps to demarcate the bedrock for constructing dam or large buildings. Also it helps us to explore the groundwater aquifers. So moving ahead, let's focus on this oil and gas exploration, because it plays a very here it plays a very major role. Like control source, like this method is developed primarily for exploring the oil and gas. So let's understand how it does. So the first part, after that, after the slide we'll see. So before that, it's a seismic diffraction method, which I mentioned earlier, that it mainly used to estimate the depth of the bedrock. It also helps in performing the hydrological study. It's also helped in demarcating the fault and fracture, and also the landfill site detection. So here you can see that when we inject the seismic energy using the active source, so and with this layer, this orange is the upper layer and the below one is the blue layer. Here you can see the velocity difference. So in general, what we get, that with depth velocity should increase, and on this refraction method is based on. So when this incident wave hit the interface between two different layers, and when the angle of incidence is equal to the critical angle, it it acts as a head wave and will continue its path. And when again this angle becomes equal to the critical angle, it emerges as a refracted wave, and that refracted wave we can we can capture using our detectors, which are geophones, if we are talking about the land survey. So here it's very pretty much evident with this. We can easily mark like by measuring their travel time and the velocity estimation, we can clearly map the depth from which the refraction we are getting. So again, this is based on the Snell's law of refraction, and the major limitation of this method is that it assumes that the velocity is increasing with respect to depth, but in real scenario this is not always possible. So whenever we encounter the low velocity layer below the high velocity layer, so this method fails. We don't receive the reflection waves. So that's why we use the reflection method, and this reflection method has been widely used in hydrocarbon exploration. So here in this GIF file, first let's understand what is the land seismic survey. So as its name suggests, that with the help of some active source, and here as we need to move deeper because hydrocarbon source can lie up to the depth of 6 kilometers, we need some high energy sound wave, so that can be produced using hammer, explosive or thumper truck. And here in this figure you can see it's a thumper truck where this heavy metal plate when hit the plate weights, it's around I think 10 to the power 3 ton or something like that, and when it hits the ground it produces the seismic wave, and these seismic waves we can capture using the geophones. And these geophones, the recorded signal, then we process that signals, and with the processing part, after processing we can interpret that signal and map the like more suitable zones where hydrocarbon can accumulate, like salt dome structures or some dipping fault where sand bodies incised, and some sedimentary rock layer where we can get the higher porosity, and velocity is decreasing, as I mentioned that this is one of the indicator for like direct indicator for mapping the hydrocarbon. So in this reflection survey, we generally try to capture the vertical motion of the ground, because as I mentioned that P waves travel, sorry, because we don't want to capture the surface wave response. So we generally consider to map the vertical motion of the ground. Similarly, in this marine seismic survey, as there is a water column, so we can't employ the geophone on the water column. So in that case, we use a hydrophone, and this is a streamer on which these hydrophones are employed. And here the seismic source, because we can't generate energy using a thumper or the hammer on the sea bottom, so for that we use a air gun, which is a very powerful very powerful seismic source, and through which we can get the response of the subsurface. And this hydrophone is based on the piezoelectric transducer, means that it converts the pressure wave that we receive at the geophone, or sorry, the hydrophone, and convert it into the electrical voltage, and that voltage can be mapped in the form of amplitude of the received seismic wave. And now moving further, let's see a few of the case study where how can we utilize these techniques to address the real problems. So first is the study, it's detection of gas chimney, and here the gas chimney act as a hydrocarbon indicator and also act as a geohazard. So in this first figure, this is an interpreted seismic section, where we can see there are mud volcanoes or the pokemark features or amplitude blanking. And I think few of you were not aware about these terminologies, but don't worry, these are just to give you a brief idea that how can we mark the geological structures or the geological features using the seismic section. So in this study, we applied a multi-layer perceptron neural network, which is an artificial neural network. And with that network, where we fed some seismic attributes which are prone to these kind of enhancing these kind of signature. So with help of that neural network, we were able to mark the gas chimney or the flow of gas migration pathways. Now, what this study helped us to understand, first thing is that there is like here you can see there is a top clover formation, and this is the reservoir zone present in this browse basin. This data is from the browse basin. So this is the known reservoir, and from this known reservoir we can easily see that there is a plume that is migrating upward and reaching up to the seabed, and due to which all these geological features that we see in this previous section uh, are getting creating. So so this is a very good understanding that how this hydrocarbon can alter the existing geological features. And this we also validated using the time section, like the we can say it's a horizontal slicing of the data, because our data is in the 3D form. So we took the time section of that, or the horizontal section of the data, and try to plot the fault. And for plotting this fault can be marked with this black lines, which is showing that similarity attribute, and for the fault zone we will get the low similarities because it's a sudden break in the feature. So when we co-render our calculated or computed gas chimney, it's perfectly matching with the existing fault network, which shows that the present fault in that area act as a conduit for gas to migrate, because for migration they need some channel or some pathway. So here the fault network present in that area act as a flow channel. And accordingly, we also took a horizontal section of the sea floor. Sea floor, it means that the top section. And here you can see some, dark depression kind of feature, or the crater kind of feature, which are nothing but poke marks. And when we again uh, co-render the calculated chimney, it's again perfectly matching well with this poke mark feature. So it's uh, it's a corroborating evidence which is suggesting that these poke marks were created from the like gas flow which is coming up to the seabed, and that's why it's a geohazard, because due to this poke marks the seafloor stability got decreased. And also, like when we are drilling, we need to understand that where is this gas zone present in the shallow subsurface, because if you are not well prepared and you hit some gas pocket, it can lead to blowout as well. So you have to be prepared beforehand drilling a well. So the purpose of showing this study, that how with the advanced tool we can effectively mark the features in a 3D sense. because earlier we were manually interpreting and manually marking all the fault present in that area. Even for fault marking also there are some machine learning application and the software that are based on the machine learning application, which are very efficient to do this kind of task. And moving ahead, this is again a very interesting study. You must have all heard about that. There are some kind of buzzwords are going like for CO2 sequestration or going towards the green energy. So this is one kind of initiative that we can take to reduce the carbon emission or to capture that existing carbon. So in this here also this seismic method plays a very crucial role. So here in this first figure, which is in the top left section, it's the A figure is a time-lapse seismic response, and from time-lapse I mean that with time we are taking again a seismic data. Suppose like today I'm taking the seismic data, and after 60 days also I am taking the seismic data, and then again after 120 days. So this is a time-lapse study that we also do in the seismic method. So first is the normal timeless seismic response, and this is again after like before injecting the CO2. So this is a simulation kind of study that has been performed by Kaur et al. 2022. So here you can see that first it's before injecting the CO2, and the B section is after injecting the CO2 after like 1530 days, and here you can clearly see the variation in the time section seismic response. Again, what they did, so to train the network, they trained their designed neural network, which is based on the deep learning. They have produced some training data set, because it's very crucial to train a neural network efficiently. So here this is their time-lapse response, and the corresponding is showing the change in saturation value of the CO2. So how, with respect to the seismic response, when the seismic response is changing, how we are getting the change with the CO2. So on that data, they have trained their neural network, and then after the training, these were the results that they were able to produce. Like first, ABC is for 180 days, and then after 630 days, they again did the simulation, and then after the 930 days. And here, the first is similarly the time response, time-lapse response section. Second is the predicted saturation by the neural network that they have employed, and C is the true saturation, that is a true result. So you can see that there is not much deviation between the predicted and the true saturation value of the CO2, and the results are very promising. So this is very good tool that can be used in future widely by all the researchers that have been working in this CO2 sequestration field. So I think this is it. I hope you liked today's lecture, and in the next lecture on next Wednesday, I'll be discussing more about the seismic method, like what are the seismic sources, how they work, and more about the physics of the seismic method. So thank you for listening. Have a good day.